Before I proceed with the next construction of the root locus topics, so let's just go back to the preliminary concepts of this root locus. Okay, so what you need to know is these two: the control system problems and vector representation of complex number. Okay, the first one, poles of open loop transfer function are easily found. We can find it by inspection, and it does not change when we change the value of gain. Whenever we change the value of k, it does not change at all. If our h is 1 unity feedback, what we have our open loop transfer function is Cg. So whenever we change the k, it will not change in the open loop transfer function. So this is open loop transfer function k2 over s plus 10. So the open loop transfer function is k2 over s plus 10 multiplied by 1. So whenever we change the value of k, open loop poles always be 0 and negative 10. Poles of closed loop transfer functions are more difficult to find. It cannot be found without factoring the closed loop system characteristic polynomial. So we have the closed loop transfer function, we take the characteristic equations, and we factorize the characteristic equation to get the closed loop poles. And another problem is that it changes with changes in system gain. Whenever we change the value of k, it will always change the value of closed loop transfer function. Okay, this is the example. This is the characteristic equations. We change the value of k, what we get is this. We get a different value of closed loop poles. Okay, so we have this diagram here, and we have the equivalent diagram on the right hand side. We have in B diagram kg over 1 plus kgh. We call this kgh here loop gain or loop transfer function. So when we want to draw root locus, we always consider this loop gain here, kgh. This is another preliminary concept that you need to understand, which is a vector representation of complex number. So okay, let's say we have this in diagram A. We have complex number here. We have at this point S-plane, and then we have this vector here with magnitude m and angle theta. We can represent this vector here is actually we have fs equals to s plus a, which from this point we have s is equal to sigma plus a, so we can put it as sigma plus a plus j omega. So this is the j omega here. Here, if we put a 0 here at negative a, so we can just represent the complex number by draw the magnitude and the angle from this 0 location. Okay, and then if we put some values in this example, let's say we have zeros at negative 7 here, s plus 7, where our s is approaching 5 plus j2 over here. Okay, this is how we represent the complex number on the S-plane. The fs is actually what we have seen in the previous example. We have s plus zi over s plus pj, where z is zeros, p is poles. So we can have s plus 1, s plus 2, s plus 3 over s plus 5, s plus 6, s plus 7, and so on and so forth. This is how we represent the complex number. And we can find the magnitude of the complex number here by dividing the product of 0, the length of 0 to the length of poles. And then we can find the theta, which is the angles, is we take the summation of 0 angles minus summation of poles angles. And try these examples to strengthen the basic concepts in this complex number or vector representation.